Hello, my name is Michal Polec and I'm gonna show you the solution of the second midterm test. In the first task, we should find a homography matrix out of a projection matrix such that the three-dimensional points on the plane with z equals 0 are mapped into the images. We can see that the regular matrix H, which does the same transformation as P for points on the plane z equals 0, is P without the third column. So H is the identity metric. In the second task we have a homography matrix with unknown parameter A, which maps let's call P ideal line to itself. We can multiply the original equations by H transpose from left and avoid computing the H inverse. The ideal line has coordinates 0, 0 and some non-zero value. If we assign the values to the equations lambda times H transpose times P prime equals P, we will get three equations where we have three unknowns. So we will get equations lambda ax equals 0 and lambda x equals x. Therefore lambda is 1. We know that x is some real non-zero value and therefore our parameter we are searching for a is equal 0. In the third task we have assigned line P and we should find line Q which is parallel to P and which meets the point X. We can simply find points P1, P2 on line P because we know that incident point with the line has dot product equals 0. Thus line P transpose times some point on this line P1 equals 0 and P transpose times P2 equals also 0. In this case we can choose for example x axis equal 1 and compute y axis, or choose the y-axis and compute the x-axis, so we will have the intersection with x and y-axis as these points P1, P2. Knowing P1, P2 points, we can draw a line in related affine plane to our real projective plane. After that, it is simple to find parallel line Q which is incident with the point x. So we can choose for example point y on Q and compute Q as a cross product of x and y points. The only way of representation of a line in three-dimensional space by three-dimensional vector I know is the perpendicular vector to the plane which is incident with line Q and point 0, 0, 1, which extends this real affine plane to real projective plane. So a three-dimensional representative is for example -1, -1, 2 vector. In the next task we should find all homography matrices which map the origin to ideal line. We know that a homography matrix does not map points to line, therefore it maps point to point, so we are looking for such a matrix which maps the origin to the ideal points. Therefore lambda times a vector a b0 equals h times 0, 0, 1, and a and b are real numbers and a or b are not equal 0. We can see that anything in the first two columns of h meet our constraints, and that the last column equals lambda a, lambda b, and 0. Therefore we will have lambda a equals h 1, 3, lambda b equals h23, 0 equals h33, where h13 and h23 are some real numbers and h13 or h23 is not equal 0 because lambda is any real non-zero value. In the last task we have two lines and 2 points which are mapped by homography matrix, and we should find all homography matrices which meet these constraints. So let's start, for example, with mapping of a line P. So lambda 1 times P prime equals H at minus transpose times P. If we multiply this equation by H transpose from left, we will get lambda 1 H transpose times P prime equals P. So you can see that lambda times the first column of H transpose, so the first row of H, equals 1, 1, 0. Therefore lambda 1 H11 equals 1, which can be also said as lambda 1 equals 1 over H11, and H21 divided by H11 equals 1, which also means that H21 equals 1 H11, and because of lambda 1 is non-zero value, we have lambda 1 times H13 equals 0, H13 equals 0. So the final matrix which we get from these constraints is H11, H21, H31, H11, H22, H32, 0, H23, H33. Let's apply the constraints for mapping a line Q to Q prime. We can use the same trick and express this constraint as lambda 2 H transpose times Q prime equals Q. If we assign the values, we will have lambda times H transpose times 0 minus 1, 1 equals 0, 0, 1. So lambda 2 times H31 minus H21 equals 0, and lambda 2 times H31 minus H22 equals 0. And we also know that lambda is again lambda 2 is again a non-zero value. Therefore the values in the brackets has to be equal 0. Therefore H31 equals H21 and H32 equals H22. So the final homography matrix from these constraints is let's call it H2, and it is composed of H11, H21, H21, H11, H22, H22, and 0, H23, H33. Now the next constraint we will apply will be for point Y. So lambda 3 times Y prime equals H times Y. So we can see that lambda 3 times 1, 0, 1 vector equals H times vector 1, 0, 1. From here we see lambda 3 equals H11, 0 equals H21 plus H23, which also said that H21 equals H23, and H11 equals H21 plus H33. So in sum we have H3 matrix, which is composed on previous constraints and which is H11, H21, H21, H11, H22, H22, and 0, H21, and H33 values. The last constraint we will apply will be for a point X and X prime. So we know that lambda 4 times X prime equals H times X. So if we assign values, we will have lambda 4 times the vector 1, 1, 2 equals H times 0, 1, 1 vector. Therefore lambda 4 is H11, H11 equals H22 plus H21, and 2H11 equals H22 plus H33. From here we can subtract the the second equation from the third one, and we will get h11 equals h33 minus h21 on, or in other words, h33 is h11 plus h21. So let's now assign h33 to the previous equation. Therefore h11 equals h21 plus h11 plus h21, and we can see that h21 equals 0. Yes, and if you look back, h33 equals h11 plus h21, where h21 is equal 0, therefore h33 equals h11. And we can celebrate because now we see what H matrix looks like. So H is H11, 0, 0, H11, and then we see from the equation H11 equals H22 plus something which is 0, that H22 is also H11, so here will be again H11 and H11, 0, 0, H11. So we will have such homography matrix with respect to one parameter, which is some real non-zero value, because we know that homography matrix has to be regular.